hello everyone. Can you hear me? Okay. I'm Srivatsa Bhat. I am a Linux kernel developer at IBM Linux Technology Center. Today I'd like to throw some light on the CPU Hotplug facility in the Linux kernel. I've worked with this particular feature on various aspects such as reliability, scalability, and some parts of its redesign also, which is happening in the community right now. So, yeah. Okay. Okay. Sure. So, this is what the agenda looks like. I'll be talking about what is CPU Hotplug and where is it used and why is it important, and some aspects of the kernel design that is there, and what is the new use cases that are coming up that are challenges to the existing design, and why do we need a redesign, and what are we going to do in the future, right? So what is CPU hot plug? Simply put, as you can relate to the words hot and plug, when the system is running, you want to add or remove CPUs, right? So that's what it means. But then you'll get into the issue of whether it's physical or logical hot plug. Physical hot plug means you actually pull out stuff, but that's not what I'm talking about today. What I'm talking about today is logical hot plug, which means when you say hot online, right, the operating system will come to know that there is another CPU that I can use, that I can schedule on, that can take interrupts, and so on. So when I say logical offline, it means I can no longer depend on that CPU. So all my dependence on that CPU should come to come to zero. That's what it means. So logical CPU hot plug is obviously the first step to do physical CPU hot plug as well. And physical CPU hot plug needs support from the firmware and the hardware. Your wiring and all should be proper to, you don't actually pull out CPUs like that. You pull out nodes, right? So I'll not get into physical hot plug. So logical hot plug has several use cases. It's not, it looks exotic, right? Why would you want to remove and add CPUs at runtime, that too? So there are use cases which I'll be talking about soon. And since CPUs are a very important resource and it has many connections, there are multiple kernel subsystems involved when you do a hot plug operation. And the latency of a hot plug operation varies between a hot online versus hot offline. And generally it's in the order of milliseconds, but based on the load it can also go up to seconds, which is okay for existing use cases, but for newer use cases this might not be so okay, which is what brings us to the challenges part later on. So as I was saying, where is hot plug really used, right? It is used in booting. For example, when you boot up, you start with one CPU. Then you eventually do an SMP boot up, where you start the rest of the CPUs. You do the init sequence and then start scheduling your tasks and things like that, SMP load balancing and so on. So during booting and shutdown, you'll use CPU hot plug, right? And then during suspend, resume, and hibernation. So if you look at the ACPI spec, right? Suspend, when you eventually, suspend resume means when you shut down, when you turn off your lid, what happens is you go into a low power state, right? So the firmware will take care of that. But before that happens, it is required that you shut down you don't use the other CPUs at all, right? The ACPI spec recommends, it's required that the moment you are going to ask the firmware to put your system to low power state, there should be only one CPU which is active and the rest of the others should be with interrupts disabled and doing nothing, right? So there are some requirements. Even hibernation and restore uses the same logic. So basically you use CPU hot plug in these areas also. Then on IBM power systems, you use it for something known as dynamic logical partitioning operations, DLPAR, which is nothing but basically IBM power systems are all virtualized. You run VMs and you have, I'll come to that later on. So basically what you do is you can mix and match CPUs at runtime to do better hardware utilization. So that is also where you can do vCPU hot plug. Then RAS, of course, that was actually the first use case of hot plug, where you find that a CPU is faulty, but you don't want to bring your running system down. You want to work around that problem. So what you do is you tell the OS, take that CPU offline, stop your dependence on that CPU, don't schedule tasks, you'll get wrong results, right? Yeah. reliability, availability, serviceability. So basically it's about, fault tolerance, debugging, that kind of facility. So, sorry. Yeah, for CPU hot plug? Yeah, so suppose you detect that a CPU is faulty, right? You don't want to, so either you can bring a server down, or you can say, you can tell the OS to offline that CPU and continue running. So that's one of the use cases, where you don't care about the performance, how much time it takes. Yeah, you can run on laptop, desktop, everything. Yes, you can. So, and for power management also. I'll not get into the platform constraints. I'll explain this later on as well. So what happens when you actually take a CPU offline? As I said, it's all logical, right? You don't plug it out. Then what will it do without task to run, right? So what you can actually do is, whenever you don't have instructions to execute, you can go to low power state. We call it C states on x86, right? So actually, if you don't have anything to do on that CPU, you go to idle state. And because you have done a hot plug and not just idle like this, right? What happens is, you don't even get interrupts. You are not the target of anything. So you can actually achieve deep idle with a CPU hot plug. So this is one way to exploit CPU hot plug for power management also. Some cases, this is important, right? You cannot just depend on a power aware scheduler sometimes. So I'll get into some details of each of these use cases, because the kernel design might not be interesting to everyone. So I'll try to, give enough importance to both the use cases and the design. Okay. So in suspend resume, as I said, so where is suspend resume used? So laptops, and of course in smartphones and tablets, because whenever your CPU, your phone is idle, to save power, it will do a suspend resume, suspend operation, right? So if you look at a suspend sequence, in Linux it would look something like this. Freeze all the tasks, don't run them anymore, right? User space task especially, then all the kernel tasks. Then invoke device driver suspend routines, right? Whatever each device has to do to put itself into low power state. So remember that suspend resume is a system-wide operation. It's not just one subsystem. So everybody has to cooperate. Eventually, we'll come to platform-specific routines, and finally, just before invoking firmware methods, as I said, you have to switch off, meaning you have to stop your dependence on the other CPUs, right? All non-boot CPUs. The boot CPU will still remain, and it is the one who is going to invoke the firmware methods. Similarly, on the other side, you'll do the reverse operation, and you'll boot up the remaining ones. So for every suspend resume operation, you'll be doing hot offline and hot online. And even tablets and smartphones are becoming, getting multi-core, are becoming multi-core, they have multi-core support. They have more and more CPUs going forward, which means if this is slow, as you scale, right, as you have more and more CPUs in your laptop or smartphones, your suspend resume gets slower and slower, which can hurt your power management, right? So this is key, one of the key use cases of CPU hot plug. Then general power management, the deep idle thing I was talking about, right? So what you can do on a large system with lot of CPUs, you can have a daemon that can calculate the system load and periodically see how much CPUs do I really need to, satisfy that load. And if it is less than a particular threshold, you can find out which CPUs to offline. Say, of course, you can look into the topology. Say, if I can offline CPUs from one socket, can I bring the entire socket to a low power state, kind of a thing. So you run some algorithm to find out which to offline, and at runtime you can take them offline and have deep idle power management. And then, of course, you can bring them back online whenever you have higher load, right? Then I was talking about DL power operations. So assume this is a power machine. You'll have a hardware like this, and L powers. L powers are nothing but virtual machines, right? Logical partitions. So you can actually, what is depicted here is virtual CPUs mapped to physical CPUs. Suppose it's dedicated like this: V1 to P1, V2 to P2, V2 P3 to P3, and so on. And the example I've given is LPAR 2, suddenly its load came down. You don't really need those many physical CPUs, 4 CPUs to back that LPAR. What you can actually do is you do a vCPU hot plug, because a OS is running in LPAR 2, which is a VM, and then move that around to this one. Here you'll see that there is a new CPU added, and probably it will serve the load better, right? So you can do better hardware utilization using DL power operations, which uses CPU hot plug internally. So that was about the use cases where we use and why is it important, right? And yeah, for the newer use case, these power management and these kinds of use cases are what are performance sensitive. These should, so suppose your load spikes, right? You should not take a lot of time to bring back CPUs online. I'm talking about servers, right? You'll have a lot of, say you want to bring back 15 CPUs online at a time. How much time will you take? Is an important factor. Whereas the original use case of RAS, somebody is faulty, you want to take him offline. So anyway, you don't want him. So you don't care about the time much, right? So, okay, let me get into the design aspects of CPU hotplug. This is non-trivial feature. This has a lot of complexity, especially because, as I said, multiple kernel subsystems are involved. So what drives CPU hotplug is callbacks. Every subsystem will have whatever needs to know of a CPU coming online or offline will register callback. That's the callback registration mechanism, right? You say, whenever a CPU is going offline, right, call me. I will do something to, fix things up or whatever is required in my subsystem. So eventually what will happen is everybody takes some action. I have depicted one action. Right, there is a set of notification. You say, okay, this is the stage. So online has multiple stages, offline has multiple stages, right? So suppose we take the down prepare operation. So this is the first notification you send when you take an CPU offline. So the hotplug core will tell, okay, this is the down prepare notification. So scheduler will stop load balancing on that CPU. So if it has a load spike on other CPUs, it won't put it on this CPU because you're supposed to take it offline. Right? Similarly, each subsystem which is interested in such a notification will take appropriate actions. Like CPU frequency device driver will stop managing the frequency aspects of that CPU and so on. Okay? So what happens is eventually everybody will take some action, right? That is what drives hotplug. That is what makes the dependence on that CPU to go to zero. Correct? Similarly, the online operation. People will start noticing, oh, okay, there is a new CPU. Let me start using it, right? That is what makes it run. So callbacks drive hotplug. And yeah, for suspend resume paths in particular, there are some extra flags. Like I said, CPU down prepare. You can say CPU down prepare frozen. Why? That's for lightweight handling. As I showed, there are a lot of operations that happen before you do a hotplug. Particularly, there are not many tasks running. So you might not have to do everything that you do on a regular hotplug. That's why you optimize it, right? You have a lightweight mechanism to say, look, you are actually in the suspend resume path. Don't do entire hotplug operation that you do generally, right? So there are some optimizations involved. And CPU offline uses stop machine, which is, I'll explain later, which is a very, very heavy atomicity. Atomic operations everybody knows, right? I mean, atomicity means you do something in an indivisible way. You don't get preempted and things like that. Which one? Correct. Hmm. Other CPUs. Good. In which one? This one? Correct. Yeah, in the suspend path. Okay, generally. Okay. Hmm. Okay. No, because there are many more CPUs possible. Say, correct. Yes, yes. Yes, you migrate the task. Exactly, yes. You have to deal with it. Yes, yes, yes. So what happens is, as I said, for example, in the down prepare notification, the scheduler stops using that CPU for new tasks, but it has existing tasks. In the next notification, it will migrate it. Yes, yes, yes. The scheduler takes care of that. Yes. That is what gives you that latency, right? That I spoke about. So yeah, particularly CPU offline has some real challenges. That's why they were using stop machine. Stop machine is like, so on one CPU you can say preempt disable or take a spin lock and have a atomic operation. Stop machine is actually what stops an entire machine. It's a special, it has other use cases, but it was used for this also. So what it does is, it runs every CPU in interrupt disabled state and keeps spinning, and only the CPU that is going offline will do some operations. I'll come to that. So that is one of the key challenges which affect current design. Okay, so let's get into locking. So I was telling, yeah, this is not a trivial thing, right? CPU hot plug. One of the reasons is because locking is kind of complex. Okay, so there is this concept of readers and writers. You can't just take a CPU offline as it is, right? There are some operations which has to be atomic. For example, if you say for each online CPU do something, right? You don't want the CPU to go on offline during that operation. You want some stability. Those are the readers. Readers prevent CPU hot plug. They say, boss, look, I am doing something really important. Don't take CPUs offline or bring them online. So those are the readers. Then writers are those that actually perform the hot plug operation, the task. Now how do you synchronize between them? So suppose the readers can block if you don't get a lock, right? If you can use a mutex model. That is called the blocking synchronization. So for that you use mutex locks with ref counting underneath. What if you simply use a mutex lock? Then what you'll do you'll end up doing is, readers will all serialize automatically. You probably don't want that. There are two readers who both want to block hot plug. They don't necessarily need to be synchronized at once. So what you do is, readers are locking allows multiple active readers. So 10 people say I don't want hot plug at this time. You block the hot plug writer. All readers can continue at the same time. If they need to have synchronization, that locking will come from outside of hot plug core. Correct? So the ref counting underneath, that is what helps you do the recursive reader locking as well as multiple active readers. And when a reader is active, writer won't be active. He'll wait. So yeah, and you can have only one active this writer. So that is the single holder lock. So it is expected that readers be infrequent. Otherwise, you'll cause writer starvation, because if you continuously have a reader stream, then you'll never allow the writer to go ahead, which is okay sometimes. Meaning the design expects that you don't have too many readers at the same time. So what if, as I said in the previous this is blocking synchronization because you use a mutex, right? If the reader can sleep, he can use this method to say don't block, don't do CPU hot plug at this point in time. But what if he is an interrupt handler or something which is atomic? You cannot say, oh, I cannot do this, so let me go and sleep. I cannot block. So if you are in atomic section, the readers can use preempt disable. I mean, this is a primitive in Linux kernel. So it's a very, very fast, heavily optimized CPU local operation. All you do is, you look up your this thing, and within that CPU you can say preempt disable. It's extremely fast. You don't wait for anybody, right? That is good. And at the writer, you use stop machine. You wait for every reader to finish that preempt disable section and then continue. That kind of a thing. Okay, so basically you run in stop machine. This is what I was trying to explain. High priority stopper threads on all CPUs. You bump off everybody on every CPU and then use that that stopper thread, which isolates the CPU that is going to go down, and run that particular CPU dying operation. So it literally stops the machine. Every CPU stops because you want to take one CPU offline, which is kind of sad. I mean, it's not the right design. But the way it was designed like this initially, because that's the easiest way to guarantee that atomicity. You cannot go wrong when everybody is not doing anything, right? You're the only person, you're the king. You can just go ahead. So this is a block diagram of online and offline. So that is the file, right? Sys devices system CPU. And for each CPU, I'll have that online file. If you say echo 1 to that, it will come online. If you say echo 0 to that, it will go offline. You can write on your laptops, and you can say dmessage to see the kernel messages. So what happens? This is the hot plug writer, because he is going to do the hot plug operation. So it will acquire the hot plug lock only if active readers are not there, because there is this reader-writer synchronization. Then, as I said, everything is driven by callbacks and notifications. So you run the CPU up prepare, tell people that you are going to do an online now. If somebody is not happy or not ready, you can abort, correct? So then once you say up prepare and everybody is happy, every subsystem is happy with the state, then you start the CPU starting notifiers with interrupts disabled. Then you run the CPU online because you are done with it. Now do the rest of the things, right? So some people don't care about the operation. They care, okay, once the CPU is online, now what should I do? That kind of a thing. Then you release the lock and continue. Whereas the case of CPU offline, similar steps, just that the notifications are different, and you also use the stop machine thing to do atomic CPU offline. So let's come. So we have seen the use cases, some of the newer use cases, as well as what is the existing design of Hotplug and why it might not be suitable. Like for example, stop machine, right? So yeah, so CPU Hotplug existing performance is bad for newer use cases like power management and so on. And there are some important reasons. So creation and destruction of per CPU K threads on every Hotplug. So what you do is there are some subsystems which have per CPU K thread. For every CPU, they'll have a K thread to do something. On every online, they'll create the thread, and every offline, they'll kill the thread. Instead, if you can just stop it and run it, right? It'll be better. So that was one of the bottlenecks. That was the reason it was bad at performance. You create, destroy all the time. Then stop machine, yeah, it's evil. You block everybody, you stop everybody with interrupts disabled for a long time and run the CPU doing notifiers. What does that mean? CPU doing notifiers, the number of them can be arbitrary. So how long will you keep interrupts disabled on all CPUs? That's just not good, right? So it can hurt workload latency. You take one CPU offline, everybody is stopped, which is not good. So yeah, reliability is also not up to the mark because everything is based on callbacks. So all the core code knows about is that I sent the notification. What happened at the other end, it doesn't know, right? It doesn't have that global view of what is happening to take the CPU offline or online. So that leads to a lot of bugs. Okay, so something goes wrong, you cannot really, walk back, and it's not easy because you don't have the global view. And there are priorities in each notification. So sometimes they screw it up, right? You say it's a higher priority notifier, but you have a special case for the notification itself that can lead, lead to race conditions and things like that. Okay, so how do we go about solving these problems? So Thomas Blexner came up with something called the K-thread park-on-park infrastructure. So you don't destroy and create per CPU K-threads on every Hotplug. You know that you're doing Hotplug pretty frequently, and you need your K-threads again, right? So all you do is stop and start, right? That will save you some performance. And stop machine free CPU Hotplug. This is one of the things that I've been working on recently. We have a design, so it's kind of not that easy because stop machine used to guarantee atomicity for you. Now you have to come up with something which will guarantee pretty much the same atomicity, but is not of the same, doesn't give you the same effect. There are ways to, if you go about thinking this problem, right? There are ways, many times, many of the solution eventually turn up to be as bad as stop machine. So you should come up with a way that is, a replacement to stop machine without being any bad on the atomicity, okay? So redesign CPU Hotplug to work without callbacks. This was again one of the ideas that came up in the community. Callbacks is one of the reasons we don't have good reliability and good control over what is happening, right? Because it's like a black box. Now suppose we can we do most of it without callbacks? I know what has to be done to be taken offline or taken online. So that is one aspect that we are looking into. And then, yeah, most of the operations in online and offline are symmetric, but some are not. So we want to make it symmetric because to have the next thing. Have multiple stages of online and offline. Now all you have is binary, right? Either it's online or it's offline. For power management kind of use cases, you might not need full offline. All you need is, okay, I don't want tasks to run, but if interrupts come, I'm going to handle it, that kind of a thing. So different stages of CPU quiescence. You can have a state machine saying, okay, I'm at full online, half the power, and so on, right? And finally offline. Then you can actually use parts of it. and be faster also for some cases of power management. So if you make the online and offline symmetric, that becomes much easier to handle. And then, yeah, bulk CPU hot plug. As I said, each of these use cases, if you see, you'll pretty much do hot plug in bulk. And not in bulk, you'll need to do, right? You take 10, say if it's a 4 CPU machine, you'll take 4 CPUs online at a time, kind of a thing. On servers, it's even much more. As I said, if there's a latency spike, a workload spike, you want to bring 10 CPUs online at a time. If you do a for loop and do a hot plug on of each CPU, that is okay. I mean, not the most efficient design. But if you can do bulk CPU hot plug, by this, what I mean is, when you send out that notification, right, you say CPU down, prepare for 10 CPUs. You don't say one CPU is going down, do something. You'll say 10 CPUs. So scheduler will stop load balancing on all those 10 CPUs at a time. So you can speed it up, right? At bulk, you do hot plug, which will speed up your suspend resume. Boot and shutdown is okay. Suspend resume is what is probably more interesting for each of us because we use smartphones and all. As I mentioned, they use suspend pretty frequently, and we are growing in number of CPUs with each hardware generation, right? What else? So once we do all this, what do we get? What is the end user benefit that you can find from this? So on mobile phones and tablets, that kind of space where the typical usage is high frequency of suspend resume cycles, you get faster suspend resume, and you will not bother about just system getting too many CPUs, which can slow down suspend resume, and yeah, faster boot up, faster shutdown, and things like that. And then obviously better power savings if you can do at runtime, right? You can take, if you have that CPU quiescence model, you can do much better power savings. On server systems, you can do faster DL power operations, which effectively mean that you'll use your hardware better because you won't think so much about doing a DL power operation. It is fast, so you can keep doing it. The other thing is RAS, and to work around faulty CPUs. One of the things that matters for this particular thing is this one: minimal impact on workload latency during hot plug. Some CPU went faulty. You don't want to hurt everybody, every CPU on that. So if you get rid of the stop machine thing, you'll actually not hurt workload latency, that kind of thing. And of course, better power savings, and you'll have a green data set. So yeah, so where does this code all live, right? So these are the main files. Kernel CPU.c is the hotplug core. SMPboot.c has the park, unpark infrastructure that I was talking about, kthread stop and start, and then the header files and things like that. And that is only the hotplug core. As I said, every subsystem, most of the subsystems are involved with hotplug. They just register callbacks and do something. So obviously all those call sites, right, they also form the hotplug sequence. So that's pretty much what I had. These are the references, and thank you very much for listening. Thank you. Questions? Yeah. Okay, what I meant is, yeah. Mm-hmm. Mm. No, 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 no. The callbacks that you register drive CPU hotplug, which makes them the writer, not the reader. Which one do you want to see? Yeah. Say CPU, say scheduler has a callback for CPU offline, right? So it's interested in knowing about a CPU going down. Why? Because it is going to cooperate with that. It is not going to say don't go down. The don't go downs, the ones who say, okay, no, wait, I'm doing something important. Don't take anything offline. Those are the ones who are the readers, right? These are the writers. The callbacks drive CPU hotplug. If this scheduler doesn't react to that notification, you cannot offline the CPU because you keep using it.
Okay, so what do you mean by there is not enough reliability?
Okay, yeah. What I meant is, yeah. Suppose some operation, one of the callbacks failed, right? How will you come back? You already sent so many callbacks, and they are all in a chain, right? So, and it's all a black box. All they can do is give you an error number. What will you do with that? Can you really send back? There are up cancelled, down cancelled kind of a notification also, but it's very difficult to manage them because they are in that global view. You have a black box at the core, which is not a good thing. If you really had view into, okay, what is happening so that I can come back, right? That is one thing. The other thing is multiple priorities and notifications. The Hotplug core designers don't write the callbacks. Some new subsystem comes up, they'll write the callback and run away. Now what will happen? You will not know whether it's designed properly or not. For example, I was talking about CPU online and offline being symmetric. They are not today. So one of the things I tried to do is reverse Hotplug notification on online versus offline. So in online, if you do steps 1, 2, 3, 4, 5, in the offline operation, ideally you should do it in the reverse order, correct? Which is not taken care of today because people can just add notifiers as they want. So this lack of global view has led to bugs, right? You really can't control if something goes wrong in between. That's the thing.
Also, the code which sends the notification waits for all the callbacks to return.
Yes.
But then the callback should be very fast. Or
Yes. Because callbacks drive Hotplug. Yeah. If scheduler takes 10 seconds to finish its callback, you're pretty much bad, right? Yeah. IPI, sorry. Uh-huh. Okay. Okay. Sure. So what he is aware of stop machine design. So the thing is, so I'll explain a little bit of stop machine design. I think I have time. So the alternative, correct? Yes. For that, for the I'll summarize this and then come to that. Okay. So stop machine, what it does is, it runs CPU stopper threads on everybody. CPU stopper threads are highest priority thread. Whatever is running will be preempted and you will run these things. And it will identify what is the CPU you want to take offline. On that CPU, you will run the CPU dying notifiers with interrupts disabled. This one. Run CPU dying notifiers on the outgoing CPU. All other CPU spin with interrupts disabled. Okay. This was the design. And this is the writer. What does the reader do? He'll just do a preempt disable, which I said is a very fast operation. This is an atomic section, correct? So suppose we want to replace stop machine because it's very heavyweight, right? So what we did is, there is an alternative known as stop one CPU. It just stops that CPU. In the sense, it runs CPU stopper thread on only that CPU, not everybody. But what happens is, there are the CPU dying notifiers, the current CPU dying notifiers expect that kind of atomic guarantee that nobody is doing anything. So one of the things is to look at the CPU dying notifiers and have appropriate fine-grained locking. If somebody is really running on the other CPU, you should take the appropriate locks. Otherwise, you won't go ahead. That is one thing. The other thing is, how do you prevent stop machine from atomic context? Here, preempt disable used to work because the only reason being, whenever you say stop machine, you'll run high priority threads, which will preempt everybody. If you say preempt disable, it won't preempt you, right? If you are in an interrupt handler and you want to say, if you say preempt disable, the CPU stopper thread cannot run, which means the CPU cannot go offline. So what we did is, the replacement should also be equally fast, right? So what we provided is a stable CPU mask. When you say stable, so we provided, so the API is something like get online CPU stable atomic, right? So what you do is, you increment a ref count. And that ref count should not be global because this was CPU local. So the ref count should also be CPU local to keep it fast. Otherwise, you'll again block on the global ref count. So you make per CPU counter, right? So once you have per CPU counters, anybody who is in atomic section who wants to block CPU hotplug will just increment that count and go, right? On the writer side, what you do is, you you have a separate mask for instead of the CPU online mask, you have a stable mask. You say you bit flip that mask. You just assume that the CPU went offline and remove it. Now you wait for every reader to complete. So these people who would have incremented the ref count, you want them to complete. So you want them to look at that stable mask once, because so all you do is you go once looking at the counters. So anytime each of the CPU counters drop to 0, that means one reader is completed. The new reader will look at the new stable mask, because you already flipped the stable mask. You want to wait for existing readers to complete. That's all. Because the new readers will anyway not depend on the new CPU. That is the design. So then you take the CPU offline. Okay.
Hi, Shrivas. One question here.
Yeah.
So during the boot up, like you said, we have one boot CPU, that is the master CPU, and then
Correct.
SMP boot will bring up the halted CPUs.
Correct.
So before that is done, if the master or the boot CPU goes faulty, so do we still have the CPU hot plug mechanism in place, or is there any stage that where it comes into picture, after which it comes into picture?
Boot CPU doesn't use CPU hot plug to come online. It's at a much later stage, right?
Okay.
CPU hot plug code runs in C. Simple example. Boot CPU has done much more assembly before coming online.
Yeah.
Right? So there's no point of, oh, you didn't say, okay, booting went bad. You said boot CPU went faulty after
Yeah.
booting.
Yeah, yeah. Before the
Before SMP booting.
Yeah, before SMP booting.
Then I'm not aware of, I don't think there is anything you can do at that point in time, because that's the only guy who could do SMP booting to offload your work, and that guy himself is faulty. So that's
Yeah,
very
I
bad.
just wanted to ask if there is any mechanism that another master would be elected at that point or something.
No, that code doesn't exist today. If you look at the current implementation, we don't do that.
Okay.
But once you do SMP boot up, then you can
Right.
deal with it.
Okay.
But not on x86, because x86 boot CPU has some special constraints that cannot go offline at all. But now people are trying to overcome that constraint. But on power system, for example, CPU 0 is no special than any other CPU once you finish your boot up. So,
Okay.
Hey,
Thank
one
you.
more doubt here. Yeah. Let's confine to one scenario where you were trying to bring down the CPUs where, say, hibernation.
okay.
So before hibernating, there were a lot of process running right now on my computer, right, laptop or anything. So who will save the process states?
Good question. Freeze all tasks. Suspend and hibernation pretty much same code sequence, except what you do at the end. Okay. Freeze all tasks. That is what saves your state. So what happens is you stop running everybody as if they were not eligible to run at all, right? So you stop all user space, because you don't have to wait for anything. Then you have kernel stuff, right? Per CPU, kernel threads, and so on. Maybe they are doing something very important and you don't want to interrupt them at that point.
Yeah,
So
from the user level, we differentiate as user process, and but to kernel, everything is a task.
No. You can still differentiate whether everything is a task. That's true. But whether it's in user mode or whether it's in kernel mode, whether it has entered with a system call or something.
Okay.
If it has entered with a system call, you wait for him to go back. Or actually what you do there is, you make everybody to enter the system. You make everybody to enter the kernel, and you make them blocked, as if you are waiting on a mutex or something like that. So everybody is blocked. All you have is yourself. You go ahead with the rest of the things.
Okay,
Then
why can't we do the same with the K threads? You said
With the?
you want K threads.
That's exactly what we do. That the K-thread park, unpark infrastructure that I talked about, right?
Yeah.
This thing.
No, before you said like K threads have to be killed again started, so it is
That's the old
overhead.
design. Yeah, that's bad. That's not good. Where was that? Yeah, see, I said issues and challenges. Creation and destruction of perceivable K threads on every hot plug is not good. It is the existing design. Just like stop machine that he spoke about. That's the existing design. For new use cases, this is not good. Right? That's just silly. You have to kill and bring them back. So the solution that has been upstream now is the park unpark, which is exactly like that. you pretty much say, you wait for me to tell you when to run next. That kind of a thing.
Yeah, but why is this differentiation happening between a process and a K thread? That is what.
Okay, so fundamentally the reason you're stopping is not suspend. That is one thing, right? The reason you're stopping here is different from the reason you're stopping there, right? This is a hot plug operation, right? There, for example, you have a special condition that you're about to freeze. So, what do I say? So the controller, so suppose there is a controller and he says, freeze is in effect, everybody go to freeze, right? In this, that is not the controller. The controller says, CPU hot plug is in effect, go to freeze, go to, stop running. So, why you should not intermingle these two is because, suppose you stop this guy with hot plug and an unfreeze happens, you'll undesirably wake this guy up because these two are fundamentally different things. Effect is same, you stop running them, but the reason why you stopped them or started them is different, right? Yeah.
Handle. Okay, that's better. Yeah, so much of what you've been talking about is how do you plug or unplug and assume it's the core level. But let's
Core
say
level in the sense?
core CPU logical core.
Okay.
Okay, and let's say that if you're basically removing the last core in a given physical processor that's attached to a socket, right? Are there additional callbacks, handlers that need to be invoked there, or does it really not matter if you're like affecting the last core in a processor
Of
versus?
say you have a 2-socket machine and you're removing the last one, right? No, not really. There are not. But if you have, so node hot plug might have things. For example, I haven't really come across any special case for at least within a socket. Say you have 2-socket machine and you're offlining the last one in, say, the first socket. That's just as good as offlining any of them. That's not a special case at all.
Okay, what happens in, let's say,
Because
in a NUMA system, right? In a NUMA system where memory is attached actually to a
yeah,
particular
that is the
socket.
thing I'm not really sure about. Yeah, if you have a non-NUMA system, SMP system, then it's equally fine because one of the reasons being, all you do is it goes to idle. You don't do anything. But on a NUMA system, it might be different. I'm not really. Correct. No, no, not kernel, x86 architecture. Intel is actually working towards overcoming those constraints. So things like some interrupts can be only given to CPU 0, or things like you cannot move this interrupt target from CPU 0. That kind of a thing. CPU 0 is special. For anything that has that might have multiple targets, sometimes we string it to CPU 0. So you cannot take that if CPU 0 is no longer to be used, that might not work right away, right? So it's an architecture constraint, not a kernel constraint. Mm-hmm. Firmware is the last. Yes, there is a dependency. Correct, correct, correct. So even hibernation also, for that matter. Oh, sorry. So what he's asking is, so the first question was about. Yeah, what he asked is this thing, CPU 0. I said CPU 0 cannot be hot plugged on x86. That is, so his question was whether it's a kernel constraint, is kernel really not good at that, or is it an architecture constraint? It is an architecture constraint, but people are trying to work around that, yes. Because CPU 0 has traditionally been the target of certain important operations. So you cannot just expect it to work just like that. But with some kernel patches, people are trying to work around that so that you can actually move things to other targets. Yes. So the other question that he asked is, suspend resume, does it have any dependency on the firmware? Of course it does. All you do till you remove your non-boot CPU is all the kernel part. including some device driver part. But after that, you have one CPU, and what do? Right? You need to kill the power. I mean, you need to drastically reduce the power, which is done by the firmware. So you call ACPI methods or whatever. Similarly, in the reverse thing, in the resume part, the first firmware gives you that control. Then so actually you store a kernel return address to invoke after the firmware gives you control here. So kernel will jump to that return address. From there, you'll continue the kernel parts, and then you'll start user space. The all tasks that will start your user space. Correct. Yes. We haven't really, designed. I mean, that's a really good question. The question is, earlier the design was, existing design is this one. For one CPU, you can say take it offline. What he's asking is, I talked about bulk CPU hot plug. Are we really going to provide a way in which you can say echo 0-4 to that file, which means, echo 0 to, and you specify the CPU masks saying take all of this offline at the same time, which is again user API design, right? You cannot break it later on, which might not be required for the suspend resume case, because in suspend resume, the user won't tell you to take CPUs offline, right? We didn't even know that, okay, suspend resume actually offline CPUs, right? It's an in-kernel function. So inside the kernel, you can still do bulk hot plug, right? If you say CPU down, that's the function you call, right? Inside the kernel, whenever at this stage, okay, I'll just 2 seconds, I'll finish this off. So at this stage, no users, you're not depending on user space. Here you can say CPU down of 0 to 4. So you can do hot plug without exposing you can do bulk hot plug without exposing a user space, sysfs interface kind of a thing. Yes. Okay. Thank you very much. Thank you.